Good afternoon, everyone. Welcome. My name is Ed Schlesinger. I'm the Benjamin T. Rome Dean of the Whiting School of Engineering. It's my pleasure to welcome you all here for this inaugural professorial lecture. This Don P. Giddens Inaugural Professorial Lecture is being held in honor of Tamer Zaki. And before I say a few words about Tamer, I want to make two observations. The first is that I can say to Tamer that everyone who is here in person is here for no other reason than to hear you speak and for your benefit. Because current COVID restrictions prevent us from even providing grab-and-go food. So sometimes the honoree might believe that people are here for the food. In your case, you are absolutely certain that everyone is here for your sake. So congratulations for that. So that's quite significant. And the other thing I wanted to say is I owe you some dinner because I can't give you any food. So nonetheless, a little bit about Tamer. Tamer joined us at Hopkins as an associate professor in the Department of Mechanical Engineering in 2013. He conducts innovative theoretical research related to the instability of fluid motion and turbulence across a range of hydro and aerodynamic applications, work that's relevant to advances in areas ranging from environmental challenges, including wind energy, to medical interventions, such as inhaled drug delivery. In addition to directing the Flow Science and Engineering Laboratory, Tamer also collaborates with colleagues in the Institute for Data Intensive Engineering and Science and the Center for Environmental and Applied Fluid Mechanics, and is affiliated with the Ralph S. O'Connor Sustainable Energy Institute. Tamer has received wide recognition for the significant contributions he's made to advancing our understanding of fluid motion and turbulence, as well as for his excellence as a teacher and mentor. Which brings me to why we're here today. Not only here to honor Tamer for his professional accomplishments and the promise we see in him, but also to honor one of my predecessors, Don Giddens, for whom our inaugural professorial lecture series is named. Don Giddens was the 5th dean of the Johns Hopkins School of Engineering, where he too was a professor of mechanical engineering who also focused on fluid mechanics. And like Tamer, whose career has been defined by commitment to research and education, so too is true of my predecessor, Dean Giddens. And now it's my pleasure to introduce Grettar Tryggvason, the Charles A. Miller Jr. Distinguished Professor and Head of Department of Mechanical Engineering. Grettar.
Okay, this is an important occasion, and we are honored to have such a distinguished visitor here who will do the real introduction of Tamer. I think I've known Howard Stone pretty much since the beginning of time. He graduated from Caltech and did a postdoctoral study at the University of Cambridge shortly thereafter before joining Harvard as a professor, where he eventually became the Nicky Josephs Professor of Engineering and Applied Mathematics. He later moved to Princeton in 2009, where he is currently the Donald R. Dixon, 69, and Elizabeth W. Dixon Professor of Mechanical and Aerospace Engineering. Howard is very well known to all of us at fluid mechanics for his wide variety of contribution in an incredibly large range of fields. He has also been a very active member of the fluid dynamics community. He has been editor, associate editor of Journal of Fluid Mechanics on many, many editorial boards, and served as the chair of the Division of Fluid Dynamics of the American Physical Society. He has been recognized in many, many ways. He was the first recipient of the GK Bachelor Prize in Fluid Mechanics. He is a member of both the National Academy of Engineering and the Academy of Sciences. He has also a long-standing interest in education and a deep commitment to diversity and inclusion. He's well known, as I said, to many of us here at Hopkins. He has also been affiliated with us for quite a while, including as a member of the External Advisory Board of the Department of Mechanical Engineering. Howard, please.
Good afternoon, I guess is the right word. And I hope you don't mind. I prepared a few remarks that I'd like to read. A little simpler for me. I'm pleased to join you for this inaugural professorial lecture. And I'd like to begin by congratulating Tamer on the promotion to full professor, which is a significant professional step that recognizes your accomplishments, fluid mechanical insights, and national, indeed international standing. In the interest of full disclosure, I've never collaborated with Tamer, so I have not had the pleasure of co-authoring a paper with him. Of course, I hope to yet have a couple of decades of opportunities ahead of me, so perhaps there'll be possibilities in the future. Pressure's on. Okay. On the other hand, I have learned from him through his published work, which is one of the beautiful features of the intellectual world we inhabit. Fluid mechanics is a discipline with wide boundaries, though most of us have relatively narrow coverage. Until a few years ago, because of a few talks I had heard him give at conferences and some papers in the literature, I had most associated Tamer with insights into important questions in turbulence. For example, the laminar turbulent boundary layer transition and the important role of pressure gradients. Perhaps we're going to hear some of that today. Indeed, he's published many papers. The number is very impressive if you go to look, exploring these and other ideas, delving into the secrets of turbulent flows in the Journal of Fluid Mechanics. I'm an associate editor of the relatively new Physical Review Fluids, so I was delighted that he is now sharing some of his outstanding work with our journal as well. So thank you on behalf of the APS. Until just a few years ago, I thought it unlikely that my interests would overlap with Tamer's, as my interests are in low Reynolds number flows, the inverse of the Reynolds number from the problems that Tamer works on. And I'm interested in complex fluids. And so that means that many of his papers are out of reach for me. However, in 2018, I co-organized a conference at Princeton on the subject of elastic turbulence, which is a fascinating set of phenomena associated with changes in flows due to polymers in solution. The polymers introduce elasticity, changes in the viscosity, and additional stresses into the fluid's response. Even some of the laminar flows are generally poorly understood. In general, the struggle in the field is understanding the coupling between the fluid and the suspended deformable polymer molecules. The flow distorts the polymer, and in turn, the polymers change the flow. In other words, understanding requires describing an underlying conformation or conformation tensor, which evolves in the flow. I did not know Tamer worked in this topic, but in fact, he was one of the key participants at the conference. He has made several pioneering and insightful contributions to the topic, including simulations and theory, and that they have brought clarity and indeed generality to the field. I recognize that time is short, so I will stop here. I'm thankful for the opportunity to join you. I'm thankful to Amtrak for getting me here on time. And once again, I want to congratulate Tamer on this professional advancement, and I look forward to watching the next steps in your career. Welcome.
Thank you, Howard and Ed, for the kind words. Today, I will share with you some aspects that intrigue me about turbulence, and specifically how turbulence emerges from seemingly laminar and organized fluid motion. And this process we call transition to turbulence. But before we start, I want to first acknowledge that this presentation is only a small sliver from a large activity by our group, and it's a group of brilliant PhD students and postdocs whose curiosity has really helped us explore a wide range of problems. So for example, some of our students are interested, indeed, their curiosity led them to look at how turbulence interact with polymers, as Howard was saying, or how the presence of a particle phase can affect turbulence, or what happens at very high speeds, and this is something that we will discuss today. But this curiosity doesn't come on its own. It comes with great mathematical skills, computational capability, and ability to interpret experimental data. So those three pillars you'll see today, theory, simulations, and data come together, and really it's their fusion together that enables us to make progress. But it's not just that, it's also the tireless pursuit of answers that the students are capable of engaging in that really has helped us achieve everything that we've accomplished. And today, this is really an acknowledgement of their work. With that, let's start. So what attracted me to Turbulence as a student was the fact that you see it in many different contexts, environmental flows, engineering flows, and often it looks as if it's inevitable and it's sporadic. It's hard to figure out where it starts. This is an example from an environmental flow where you have a river and it seems nice and quiet and suddenly it becomes turbulent. This is another example where you have smoke going through a screen and all of a sudden there's turbulence. And here, this is the wake of a single or a tip vortex of a single wing turbine, and suddenly there is turbulence. So even though the final outcome always seems to be turbulence, each of these examples has a certain process that takes you from the laminar organized state, and this turbulence that is lurking in the background comes about. Our group has spent a lot of time working on boundary layers. So boundary layers are those really thin regions that are around objects that are immersed in a fluid. So if you think of a wing of an aircraft, if you think of an underwater vehicle, a submarine, if you have one, or if you think of a car on the highway, relative to the car, there is wind moving around the object, and there is a boundary layer where the velocity of the fluid relative to the object has to go from the free stream velocity to 0. This thin boundary layer has significant implication on fuel consumption, has significant implications on our environment. So what does this boundary layer looks like? So you can think of high velocity fluid away relative to the object, away from the object, and then 0 relative velocity on the surface. And this here would be what we call a laminar organized boundary layer. But inevitably, you get turbulence, and turbulence mixes. So it mixes the high-speed fluid with the low-speed fluid, and you get a fuller profile. Well, this fuller profile means you have stronger traction onto the surface. And if you have stronger traction, you have higher stresses, and you have a higher fuel consumption and an impact on the environment. You also have increased not just momentum mixing, but also heat transfer rates. This cartoon has behind it a much richer picture. So if we zoom in onto this airfoil, and you think of it, so now we're very close to the airfoil or the hydrofoil, and you have this laminar flow, and behind it, there might be some perturbations, but it looks nice and organized. And then downstream, you see this, actually, this profile that we drew has all these chaotic motions within it. And what we have here is the average. If you want to plot the surface traction or the surface stress, you can see initially it's at a laminar level, and here you can see these strong fluctuations. You can see how strong they are compared to their mean. They're very large fluctuations, and they give you this turbulent behavior. And in between, this is what we call laminar to turbulent transition. If you look at the airfoil from the top, you have this view where you have, so now you're looking at the flow over the surface. It's laminar here, it's turbulent here, and in between there is these bursts of turbulence. So what are the implications of this laminar to turbulent transition process? Why is it so important? Well, you can think about any flow regime of interest and see what implication it has. So we start at the very high speed, and we're talking here about hypersonic flows that are moving much faster than the speed of sound. And whether you're interested in national security or interested in space exploration and reentry vehicles, laminar to turbulent transition is a primary design consideration. If you have an accurate prediction of laminar turbulent transition, you can ensure that your vehicle is safe, and we'll talk about a bit more, and that it has the range that you designed for. If you cannot accurately predict laminar turbulent transition, you risk losing the vehicle entirely. Civil aviation, another area that is important. Much of the drag on the aircraft, 30 to 50% of the total drag, is due to this traction onto the surface. So this here is the drag distribution on the aircraft. Half of it roughly is lift dependent drag. So if you want to be able to fly, you have to pay this price. And then in addition, there's this friction drag. If you want to look at the wings, this friction drag, half of it comes from the wing. And if you can design wings that maintain laminar flow, you can have a significant impact on drag on aircraft. Now multiply that by the number of aircraft that take off every day in non-pandemic times, and you can see how significant the impacts would be. Even if you zoom in within the engine, you have this fan, and behind the fan, there are all the compressor stages and the turbine stages, and every single one of these blades, looks like an airfoil, has a boundary layer around it that may be fully turbulent by maybe going from a laminar to turbulent transition. And again, this transition process has implications on performance. It has implication on whether your compressor stalls, whether the turbine is too heavy for the design. So how do we study these problems? We tend to do theory and computations. And most recently, we've been combining also our work with experiments, as we'll see today. So if you think of the boundary layer, this is a flat plate, and you think of the flow next to it, you can think of it as a sheet, basically a membrane next to it. And you can think of it as the sheet has an instability. In fact, theoretically, you can perturb the flow next to the surface, and you can predict that it has this instability that travels downstream like it would on a membrane. So you can predict this instability. In fact, you can extract this here and say, well, I can do a secondary instability analysis, and I can predict the secondary panel pattern that emerges. And you can have predictions all the way from here to here. And then all of a sudden, you have to get to this stage where you have turbulence, and you cannot do theory anymore. You have to do numerical simulations. So this here is a numerical simulation that solves the governing equations on a supercomputer to be able to generate this prediction. The theory dates back decades, and for a long time, we couldn't reproduce it experimentally. It took over a decade to be able to measure this experimentally. And the difficulty in actually realizing the theory in the lab is that no experiment is so clean, without uncertainty. There are always uncertainties in the lab, and those uncertainties really bypass this mechanism entirely, generate a completely different transition scenario. So it's called bypass transition, and basically you have background disturbances. Those background disturbances interact with the near wall region, this boundary layer, and generate completely different flow patterns. So what you always observe in reality in engineering flows tends to be what we call bypass transition. And the theoretician used to say it bypasses theory, but now we have theory to explain it. In fact, we've developed this theory where we can look at the environmental disturbances and ask ourselves for every single frequency in the environmental disturbance. So this here is a measure of the environmental disturbance. Is it low frequency or high frequency? We can evaluate whether, relative to the disturbance, the boundary layer looks like a very deep layer or it looks shallow, right? Based on the size of the disturbance, if the disturbance is very long, and this is an example of a long disturbance, relative to that disturbance, the boundary layer looks shallow. And if the disturbance is small scale, like what we see here, relative to that, the boundary layer, no matter how thin it is, might look very deep because the disturbance is small. And we also look at the viscous scales and ask, is this disturbance going to penetrate or is going to die? So we can take environmental disturbance, and using really beautiful theory, we can determine whether disturbances will affect the boundary layer or not. And we were able to predict these long patterns and have a sense of how these environmental uncertainties can affect the flow. And we extended this theory to viscoelasticity and other configurations. And then you can take this and actually go to the engineering. So you start with canonical, and then you go to the engineering flow. This here is a passage in that complicated compressor or jet engine that you saw. And this here are two blades from the engine and the flow in between going through. And again, you could see that the turbulence in between has all sorts of scale, and you could see these elongated patterns inside that boundary layer, and we can make predictions about how this will behave. But truly, if you want to demonstrate that you are predictive, it's not enough to just simulate the flow or do an experiment. Can we actually predict in this boundary layer which particular structure of these elongated structures will lead to turbulence? You can see if you zoom into the boundary layer, you have all these structures that emerge because you have uncertainty in your environment. And the question is, can we, using theory, predict which particular one of these long structures will ultimately lead to turbulence? And the answer is very simple. I teach the answer in my hydrodynamic stability class. It's a simple stability problem. If you have a system where you have a bowl and inside that you have a sphere, you know that this is stable because if you perturb the sphere, it goes back to the center. And if your system looks like this, you have a bowl and on top of it, you put a sphere. If you perturb it, it will fall because it's unstable. But of course, we're fluid dynamicists, so it's not so simple. We actually have to solve this set of equations. So it's partial differential equations, and they're all coupled, and you form a big eigenvalue problem and find those eigenvalues and eigenfunctions, and they tell you whether your flow is stable or unstable. So can you do this for such a complicated configuration? And indeed, we can. We extract the flow from this in this two-dimensional plane, and we do this stability analysis. We slightly perturb it and see, can we predict whether it will be stable or unstable? And after we do this, we repeat the process over and over again, and we try to track our prediction and compare it to reality. Can we actually pinpoint the particular instability or unstable flow structure to understand the origin of turbulence? So we do that, and here's what we find. So if you take this cross-cut of the flow, so this is the cross-flow plane, the flow is moving into this board, into the screen, and this here is low and high-speed fluid moving through, and our analysis predicts that there's this location in the flow that is unstable, and it's exactly this location, and we're zoomed in here, that leads to this onset of turbulence. In fact, our analysis tells us exactly how turbulence comes about. What is the prediction? Well, the prediction is that if you look at the flow from the top, here, our prediction says, well, you're going to have span-wise oscillation. This is a span-wise velocity that is going to push the flow to the right and to the left. It will have it meander. And also, this is the span-wise velocity, and it would also twist it. And this meandering and twisting of the flow will ultimately lead to chaos. So we go to a calculation of the full governing equations without the theory now. And let's see what happens in this calculation. These are all the flow structures, and we're zooming on to one of them. And let's see if this one will indeed meander and be twisted like the theory suggests. And you can see how this pattern emerges. And the theory is actually very good at predicting the onset of turbulence. So now we have access to all the details. In fact, the theory helped us understand some of the observations in the simulations that we couldn't, without aid of the theory, be able to pinpoint. Okay, so this was one event, but if you work in turbulence, you know that it's statistical, and if you want to make predictions and be able to trust them, you have to show statistical accuracy. So what we've done is we performed very long calculations and extracted hundreds of events and studied them. So again, this is a top view of the flow next to this plane. And this here are the long structures, and these are the spots. So we developed algorithms that are now widely used to discriminate between the laminar flow and the turbulent region. So this is an exercise in laminar turbulent discrimination. We've generated algorithms that are physics-based and are ones that use machine learning techniques. And we're able to extract these localized patches of turbulence, nascent turbulent spots, young turbulence, and analyze it in detail. And here's an example of one of them. What's remarkable is with Charles Menneveau and one of our postdocs, we looked at statistics of this interface between the laminar flow and these nascent turbulent spots. And we were able to demonstrate that the interface has this fractal dimension that is characteristic of very high Reynolds number turbulence, but now you have it in this microcosm of turbulence when it's first born. Also, with our colleague Greg Einken, applied math and statistics, we were able to use his beautiful theory, mathematical theory, to explain why the surface tractions increase at the first instant that one of these spots touches the wall. And what's also remarkable, if you look at the evolution of these spots, they all have the same growth rate in time, even though they come from many different simulations with different flow conditions. And if we go about their origin, what we've done, we were able to extract all the structures in these simulations and look at a PDF, a probability density function of their evolution. So these are all the low frequency structures within this flow. We can extract them, we can study them, and every single time one of them becomes a turbulent patch, we can identify it in this map. And our theory can with statistical accuracy, predict every single one of these events. It's great, but our theory is computationally very expensive and requires significant expertise to be able to execute. How can we make it accessible? So our students used the information they gathered from the theory to take features from these streaks that are easy to identify, build machine learning algorithms to be able to accurately predict them, and to do so very quickly. So these features of the streaks are, for example, their intensity, their momentum they carry, and you can make accuracy predictions. So this says we can make predictions that are 75% accurate from a single feature of these streaks. And if you combine the different features, you can get to 90% accuracy. So our theory is slightly more accurate than these machine learning algorithms, but there's a big difference. If we actually simulate the flow, each breakdown event takes about 10 to the 5 seconds. So it takes about a day on a single CPU. And if you want to do larger calculations, you can use, and hundreds of events, you can use a supercomputer to accelerate this procedure. But this here is the full calculation. If you want to use our stability theory to be able to predict the instabilities, you can bring this down to a couple of minutes. And if you want to use our machine learning algorithm, you can bring this down to 0.1 seconds. And on new architecture, you can probably accelerate it. So you can see here the entire journey from theory combined with simulation and ultimately machine learning algorithms to be able to make predictions, understand them, and be able to accelerate them. So then when you take all this knowledge and say, well, let's challenge ourselves to take this what we've learned and go to high speeds in extreme regimes. And really the future of our research is in this direction. Can we make prediction then at very high speed? So this is in extreme environments. We're looking at re-entry. So this is a picture of Discovery, and this here is a picture of Columbia. The only thing that is certain in this flight regime is that there are many uncertainties. That's the only thing that is guaranteed, the uncertainty. And any miscalculation is potentially catastrophic. This picture of Columbia is an infrared image that shows you basically the blue here means low heat flux, and the red here means excessive heating due to turbulence. If turbulence takes place, for example, early upstream, you can lose the shuttle. In fact, Columbia and the entire, this orbiter had many different instances where there was recorded very high heat flux and much higher temperature than design conditions. And we ultimately lost Columbia due to damage on the wing. So 2.5 years after Columbia, we had Discovery returned to flight in 2005. And that was a very exciting time for me as a fluid dynamicist working on transition. And this idea that uncertainty and the lack of data can be such a significant challenge was never as true as it was with the Discovery mission. So this is a timeline of Discovery. Discovery was in orbit for about 13 days, and some hours, has done over 200 orbits around the Earth, and it was due to return. When Discovery was doing the rendezvous pitch maneuver, they took images of it, and these images were discussed on July 28th, 2005. And this is a picture face on. You can see the belly of the orbiter, and they had what they called at the time a area of interest. And this area of interest is a protruding gap filler between two ceramic tiles that are part of the heat shield, and you have this protrusion in the middle. And you can see it here. After 3 days of scientists at national labs and at NASA working and doing analysis, so from July 28th to August 1st, this area of interest became an issue. So in this interview, I want you to listen to how many times uncertainty and lack of data is emphasized.
And it's really that lack of data which adds to the context of this uncertainty. In working through the binary transition predictions, if you want to call it that, for this particular topic, that was one of the primary difficulties we ran into. And the tools and methodologies that we have put into place were showing us that we had a wide range of uncertainty because in part of the small amount of flight data we've got available, not a good coverage in the flight data, not a real strong understanding of what happens with these topics at really high altitudes. And that all feeds into this story of uncertainty. And if we're going to make the vehicle safe and the crew safe, when we've got that level of uncertainty, the right thing to do is to do this repair.
Okay, so you could see the biggest issue is uncertainty. July 27th, they thought it will not be a problem. The 28th, they said the images and they will investigate. 3 days later, the nation's best scientists, and due to the uncertainty, they decide to do the repair. And the repair was done on August 3rd. This is Stephen Robinson that you will see who did a spacewalk to do the repair. All right, so the story is one of uncertainty and lack of data. If you want to work in this flight regime, you have to be able to handle uncertainty and lack of data. And we're not going to do Mach 8, 17, or 18. We're going to drop down to Mach 4 and Mach 10. So we're not going to have some of the effects that you see in this that are related to the space shuttle, but you'll see what our group is doing to mitigate uncertainty and to deal with the lack of data. So why is this flight regime so challenging? Why is it when you go to high Mach numbers above 4, all of a sudden the problem becomes much more difficult? Well, for low Mach number, we had these two scenarios, orderly and bypass. When you go to high Mach numbers, situation becomes really messy very quickly. If this is distance along a flight vehicle, let's say, and these are frequencies, everything inside the black and the blue regions are unstable frequencies. So you have a wide range of potential instabilities. And it's very difficult to predict what you will encounter in flight. It could be any combination of these frequencies, and the relative amplitude matters. To give you a sense of how sensitive this problem can be, these are two simulations. Each of them is forced by one unstable frequency, the same one. We're basically perturbing the flow at the same frequency. And we take 1% of the energy, and here we put it in some noise, and here we put it in some colored noise. So it has a particular frequency choices. And early on, they're hardly distinguishable. But if you look, ultimately what happens, you can see a significant difference in traction on the surface or shear stress. There's a significant difference on heating. The one case, you have this laminar to turbulent transition very far downstream. In the other case, it's very abrupt. The difference, if your TPS, your thermal protection system starts here, you're doomed. Okay, so sensitivity, to less than 1% of your energy content. How do you design in these conditions? So you go and look in the literature, what people have done before us, and you can see, okay, well, where does the flow become turbulent as a function of the environmental disturbance energy? And these are data from a lot of our colleagues, and it's all over the place. You really cannot pinpoint, you cannot say at this level of disturbance energy, transition happens at any particular location. So what we decided to do is to draw a line in the sand and say, we are going to find out for a given level of energy, what is the earliest location transition can take place. And this is a very challenging problem because of these sensitivities, and also because transition is a nonlinear phenomena. So it's not trivial being able to draw this line in the sand. But once you do, you can guarantee that in flight, any disturbance with this level of energy will never cause transition upstream of this line. It will always be downstream. And if you design based on this line, then you can, again, try to come up with strategy to push the line downstream. So you can come up with new design that can delay this line as much as possible. So how do we do this? Well, we solve a very large optimization problem. What we're looking for, if we have a disturbance, if we know the disturbance, we can solve the Navier-Stokes equations. It's difficult, it's challenging, but we have supercomputers. So we can solve the Navier-Stokes equation and predict the entire flow. So the task is to loop over all possible disturbances that we could ever encounter. For each of them, solve the Navier-Stokes equation, find the flow, and find the worst case scenario. So this is a nonlinear optimization problem. So if I go back and forth, this is the first perturbation, and if I modify it, I might find an upstream transition location, and I keep doing this over and over again until I find the worst case scenario. Okay, how do we actually do this in reality? Because this optimization is very expensive. Well, we start somewhere. We say, these are all the frequencies that are unstable, and let's give them all the same amount of energy. And then we find that, okay, laminar to turbulent transition happens at some location. But we don't just start with one point. We generate an ensemble of possible solutions around this one. And for each of them, we will do a numerical calculation that requires thousands of cores working together for hours, and we can make these predictions. So you basically have a point in your cost function space and a few points around it. And from this, you learn which combination will promote transition to turbulence, and this gives you your next guess. So you move in that direction, and indeed, if you move in that direction, you have a more dangerous situation. And then you generate a new ensemble that gives you a sense of how things change, and then that gives you the next guess, and so on. So you do this, and this optimization is performed over this particular one over 800 dimensional space. So if you think if you're on a mountain and trying to find the bottom of the mountain, that's a much smaller dimensional space than 800 dimensions. But here we are, we can do this, and we can discover the worst possible condition. And if you design based on that, you can guarantee safety. So we've done this procedure, and we've done this optimization, and we found this spectrum. So this here is the frequency of the perturbation, and this is its span-wise wave number. And what this plot tells you is that there is a particular distribution of energy, and the three most important frequencies are these three here. And this is the relative amplitude. If you ever encounter this disturbance, this combination of waves, it will give you the most dangerous scenario, the earliest possible transition location. Any other flight disturbance that you encounter will be relatively benign. Now, when you look at the evolution, this is what happens in the flow. This is away from the wall and then closer to the wall. And this here is a side view. You can see here, you have these acoustic waves very next to the wall. This is a very high Mach number, 4.5. You have these acoustic waves, and you have these rope-like structures that ultimately break down. What is unique about this is that none of the mechanisms in the literature that people have been studying, that we concoct based on theory, linear theory, have ever examined this transition mechanism. But this here is entirely based on nonlinear interactions between a triad of waves. Their nonlinear interactions, every pair will interact and generate another wave and so on, leads to the fastest route to turbulence. And once you know that, you can devise ways to eliminate this route to turbulence, and then you have a robust design. So what we've done is we've used the knowledge from these calculations to design roughness elements, surface texture, that while people might think roughness is always destabilizing, this particular roughness that we've optimized to address the worst case transition scenario actually delays transition. This is the canonical, the case that we've discovered, the worst case scenario. And once you introduce this roughness element, you can entirely eliminate transition to turbulence in this high Mach number flow. And you do that by essentially disturbing these acoustic waves that are traveling near the wall, basically by changing their phase relationship with the outer flow, and you can stabilize the flow entirely. So this is our strategy for being able to deal with uncertainty. You need to be able to make robust design choices. So how do you deal with the lack of data then? Well, these are all numerical predictions. Well, how do we deal with the lack of data? Well, there are two approaches. One is to do experiments, and one is to do these very expensive calculations that we do. And if you look at experiments in high Mach number regimes, these are facilities that are operating at very high pressures. They tend to be very bulky pieces of metal with very little access. And this is an experiment from the Air Force Research Lab, flow over a cone. There are a lot of uncertainty about the environment within this experiment. And what you would get out of it is oftentimes just limited to a few measurements of pressure on the surface. That is all you get out of this experiment. At least that's what we were told earlier. And then you'll see what it turns out they had more. And in simulations, we also make assumptions. We might have a model of the governing equations at a different level of fidelity than you should. You make assumptions about what the environmental disturbance is. And usually we do both of them and we say they're complementary. If you go in this Mach number regime and compare the experiment and the simulation and the literature, errors as large as 100% for the minimum value. So they report minimum errors of 100% in the pressure, and they're satisfied. What we've decided to do in our group is actually quantitatively compare the measurements from the experiment with our model predictions. So you put them together, you compare them, you subtract them in a cost function, and then you optimize. You keep updating the uncertain parameters in our simulations, and you do this iteratively. You keep updating the environmental disturbance until the simulation predictions match exactly the measurement from the experiment. Now, it's a nice idea, but you have to be careful. Why? Because these flows, these transitional flows are chaotic. So they're very sensitive to uncertainty. We know that. So accurate interpretation of the measurement is challenging because of chaos. We have a sense of chaos from the butterfly effect. If you think of a cell where you have, this is a hot wall and this is a cool wall, and you get a convection cell inside between the hot and the cold wall, this is called the Lorentz system. And this cell is chaotic. And this here is a prediction of the state of the system. If you have a very small difference between the two systems, so this is one system and this is another system, and there's between them a difference, which is the flap of the butterfly wing. The two predictions are initially the same, and then they deviate from one another. So let me play it. You cannot see the difference between these two systems initially because it is the butterfly flap of the butterfly wing. And you can see they oscillate, and then all of a sudden they'll become chaotic and then diverge from one another. And now you can see the difference. So these systems are chaotic. Laminar to turbulent transition is chaotic. And as such, being able to have our simulation match the experiment is very difficult. But what I promised to tell you about today is the reverse butterfly effect. And what is the reverse butterfly effect? Well, we only have measurements. You have these measurements and you want to go back and discover where they came from. And I will tell you to trust me, we found where they come from. And then when you tell me, okay, well, what was the truth that generated this measurement? And you look at it and it turns out, well, actually the truth is very different from our prediction. You can see this truth started very far away from our prediction. And then they both synchronize from some time, and then they go apart. So you have to be very careful when you're interpreting measurements because there are non-unique solutions. Those measurements could have come from many different initial conditions. But the idea is, here's the prediction and here's the truth. They're very far apart from one another. And then you can see they're quickly synchronized, and then ultimately they'll move apart. So these are some of the challenges that you have to be aware of when you're solving these inverse problems, going from measurements to data. So now they're nicely synchronized, and then they will diverge again. Okay, so let me tell you the story about the data we received. We were given data at Mach 6 and Reynolds number 7 million per meter. That's how experimentalists like to call it. And we don't know the environmental disturbance. We want to be able to discover it. And the data we have are wall pressure signals. Basically, we have 1.2 millisecond of data at 6 probes. And today we're only going to focus on 4 of those probes. Can we figure out where this data came from, or what was the condition in the tunnel? You can think of, we're interested in the statistics of the flow condition. So you think about spectra. We're not interested in a particular event. We just want to know on average what is the condition in the tunnel. Or there might be an event of interest, and you want to be able to predict exactly what generated it. So we do that. We formulate our optimization problem, and we try to basically minimize the cost, which is the difference between the measurement and our prediction of the measurement, and in the process discover the environmental condition that generated this flow. So this is our cost function that hopefully will drop as we continue to improve our estimate. And these are the experimental spectra, and the gray line is our starting point. And as we iterate, you can see we improve the prediction. Just bear in mind that the minimum errors that other people have in their prediction is 100%. So you could see that we're doing reasonably well in ours. How about the particular event? This is the particular event of interest. The same procedure. We have a cost that we try to reduce, which is the difference between these measurements and our prediction in gray. And we're trying to predict the environmental condition, both the amplitude and phases of the disturbances. And we can do that. So it turns out our colleague who gave us the data also had in his back pocket some data for Schliering imaging of the flow, which he had not told us about. And after we made our prediction, he said, well, let's see how good they really are. Let's compare them to my Schliering. And this is a Schliering imaging, and this is the particular event here highlighted that we were trying to represent. I would assert that our predictions are much cleaner, at least that. So you can see we predict the wave packet that has actually generated this event, and we're continuing to advance these findings. Now, what is the opportunity here with these tools? Well, first you have to recognize that going from the measurements to the entire flow, what we've decided to accept is that the measurement, we're not trying to measure exactly what we're interested in, the quantity of interest. If you're interested in vorticity of the flow or the kinetic energy of the flow, you're not trying to measure exactly the quantity of interest. No, the measurements are an encoding of everything that happened in the flow before you got the measurement. My students are very good at finding barbecues. When they smell it, they don't think, oh, I smell barbecue. No, they know where it came from, and they can trace back and find it. It's the same with these measurements. Sensors are not just a record that you just accept as it is. You have to be able to decode it and figure out where they came from. And if you do that, well, you basically can go from the measurements to the entire flow field. So now your sensors have this super resolution that that you can discover. And now you can work with your experimental colleagues and do things that are different from how we approach these flows. It's not about placing the PCB sensors to get pressure data exactly where we want to measure the pressure. No, it's placing them such that we can minimize the uncertainty in being able to discover the entire flow field. So we've done that numerically to demonstrate this idea. We basically looked at this cost function, and this is the difference between the measurements in the tunnel and our simulation, and we said, well, how can we, this cost function looks like this. It's very difficult to minimize it, to minimize the difference, because it's a very difficult landscape. You're trying to find the environmental disturbance that minimizes the difference between the experiment and the simulation. So basically, you're trying to find the minimum of dysfunction. It's very difficult. But what if we can change it? What if we can weigh the measurement in a way, so put weights on different sensors, say these sensors are more important than these sensors, and be able to manipulate this landscape entirely and change it into a much easier problem to solve. Okay, so this is the measurement weighting. You can also do optimal placement of measurements. And we've done that. We looked at different weighting strategies. And if you properly weigh the measurements, this here is weighing the turbulent region, this is weighing the intermediate, and this is weighing the laminar region. You could look at different weightings, and we have theory to explain what's the best weighting to improve this solution of this inverse problem. And this here is the cost function, how it converges if you just accept all the sensors to be equal, versus if you recognize that some sensors actually have this ability to minimize uncertainty in your prediction. So if you have the optimal weighting, you can have a much more robust prediction. And we've done this in a computational setting where the measurements or observation came from an independent calculation. And I just want to show you how remarkable is the prediction. This here is the hidden truth that gave us some wall pressure data. And this is our prediction of the hidden truth. So you can see how remarkably close they are. And of course, these simulations are very expensive. They require thousands of CPUs working together for hundreds of hours and doing this optimization problem. So the natural step is to use machine learning to be able to accelerate these procedures. And in a project with George Karniadakis at Brown and Charles Menouveau, we trained operator networks to go from sensor measurements and be able to predict the environmental disturbance. And now the training becomes very expensive because you have to generate all this data for training, but then the predictions become very quick, so you can actually use it. And then once you have the environmental disturbance, you can also train networks to predict what the flow would look like. And we've taken this to higher Mach numbers. So this is a Mach 10, where you have dissociation of chemical species. And if you can spot it, this here is 5 orders of magnitude smaller perturbations than the mean flow. So these are very accurate predictions. Now, all of this is possible because of the effort of the brilliant students and postdocs in the group. We're continuing our work on high-speed hypersonic flows. Really, these extreme flow regimes are the frontier. And David is the most senior member of the group, and these fearless students behind him. David really is a wonderful contributor. He's always willing to do one more iteration, and I really mean that. We do a lot of one more iterations. And then Mengza is asking similar questions, but not in the transitional regime. He is asking these questions for turbulence itself, fully turbulent flow. He's asking, what is the minimum resolution that I need of measurements to be able to predict everything in between these measurements? And he can predict fully turbulent flows down to the smallest scales with accuracy. And then we are also going to very high Reynolds number, where experiments alone or simulations are not enough, and we're combining them together. Mitchell is doing some modeling work, and Yifan is our code warrior. He's really developing the tools to be able to merge computations and experiment at the highest Reynolds number. And Professor Joe Cass is doing the experiment at the world's largest cavitation channel facility. And we're asking questions about how compliant surfaces affect this interaction with turbulence. And we have a team of students who are very good at finding the barbecue. They're very good at taking sensor data and being able to figure out where are the remote sources that generated these sensors data. So as a group, in summary, we really have a brilliant team of researchers, and I'm here today to acknowledge their contribution, really. And they've learned how to combine theoretical predictions and high fidelity simulations and measurements, because they recognize that the way to make an impact is not with each of these tools separately, but rather by integrating and fusing them. So when you integrate measurement with simulations. And with that, I thank you, and I'll happily take any questions.
Thank you, Tamer. Questions from the audience? Jim. Come back here.
So you showed that example of putting the divot sort of in the channel across where you killed the turbulence. I'm just kind of I'm curious, from an aircraft design or a vehicle design, perspective, what is this tell us in terms of getting lower drag performance out of our system? Do those have to be so finely tuned to the velocity that they're not that useful, or there's some places where they're
There are places on the aircraft where.
Can I ask you to repeat
Okay.
the question so the audience or the remote?
Absolutely. So the question is about introducing surface topography to be able to delay transition. And it's basically this example here where we were able to design the surface roughness to make sure you can delay transition. When you have a design like this, the key is whether it is effective for a large speed range or a particular flight speed. You don't want, also over time, this will change shape and you don't want it to have a detrimental effect. So again, it's a question of robustness. You need to be able to make sure that there's no sensitivity to variations, either in the flight speed or in your design. So those considerations you actually have to take into account. Absolutely.
Yeah, it turns out my question was related, but slightly different. This is a prediction for what you could do to a surface to eliminate an effect.
Mm-hmm.
Has anyone tried to check it experimentally?
So I'm spending time at APL this spring, so hopefully we'll be able to do that. But there have been experiments showing that you can design you can use roughness to delay transition. But what they found in the experiment at Purdue in the Quiet Tunnel is that the roughness they introduced was ad hoc. They said, oh, let's just take a hemisphere and put it. And what they found is that they can delay one type of instability wave, but then they generate other instability waves. So it becomes that question, could you have an unintended effect? But with these here, we believe there is no unintended effect because we can look at the spectrum of the flow and it looks nice and clean.
Thank you. More, Kevin.
Yes, Kevin.
Beautiful presentation.
Thank
You
you.
mentioned flow a lot, but I didn't hear you say temperature, and I know they're both connected. So are they in your simulations, or is that what you're going to do next year?
No, temperatures are in the calculation. All the calculations we have account for basically all the hydro and aerodynamics and aerothermal dynamics. Yeah, so we have temperature is a big part of it. A lot of those blue contours that you were looking at, those are actually heat flux contours on the surface.
Great talk, Tamer.
Thanks,
Thank you.
Charles.
I just a little comment on the video you showed at the beginning. I guess I was thrilled to see on C-SPAN the word boundary layer. You were thrilled with uncertainty, but I think it was great to see boundary layer mentioned there. And the astronaut who fixed the tile, Robinson, I guess you probably know, right? He was a PhD student at Stanford and wrote a whole thesis on all possible structures in turbulent boundary layers, then became an astronaut, and that was the guy who actually fixed that tile.
Yeah, and
I guess my question was, he seemed to have removed the perturbation from the shuttle, and of course they made it. I guess they made it back safely. But so that would, that's sort of opposite to the effect that you just mentioned. I wonder if you have any comments on that.
so that roughness was protruding 1.2 inches out of the shuttle. So that roughness looks like an obstacle that will promote turbulence, and then you would have premature turbulence that will ultimately lead to excessive heating and potentially catastrophic effects. It was not optimally designed roughness.
No.
I apologize if I have to repeat this. It was right around the time that my brain was turning to turbulent flow in your talk, but I wanted to follow up on Jim's question because it seemed
like, if I'm understanding right, you're saying basically design this patch to be kind of like a spatiotemporal notch filter to sort of get rid of the frequency that leads to the early. Is that the right way to think about it? Like kind of like system theory filtering kind of perspective?
So what it does is indeed it filters a frequency that would normally lead to nonlinear interactions and then turbulence.
But it rejects that frequency somehow.
It actually has it propagate its energy away from the boundary layer. So what it does, it redirects its energy away from the boundary layer.
So let's thank, okay, one more question. Hang on. There's no food, so we might as well ask.
So lovely, Tamer, thank you. The dumb thought is if you have something that there's separation of time scales, there's lots and lots of conditions that in a very short time end up giving you the same thing. And you kind of mentioned that, and my gut feeling would be this is unresolvable. I mean, if there is infinite things that collapse very quickly to the same thing, you can't get them. So comment on it.
So it's true. So first of all, you have to do, you have to provide variances on your predictions. So we do basically, we have the posterior statistics to look at, we have these predictions and how much variance do we have given uncertainty in these predictions. So we predict the flow and then we look at the statistics around our prediction.
Thanks, Ed, for one more question. So I was wondering, you're thinking about the planetary reentry problem, and then you're doing lab experiments. How much does the chemistry matter, right? So you're coming in way up there, and then you're looking down.
So yeah, so the example that I showed with reentry, where obviously dissociation on formation of plasma is important. The lab experiment, these are Mach 4 to 6 and so on. There's no dissociation, there's no, basically plasma, none of that is present. The reason people look at this range is because that's when the instabilities without the chemistry start to become important, the same instabilities. And then, of course, if you want to do thermochemical effects, then you have to go to higher Mach numbers. So we then, for that, we're doing Mach 10 and so on. But then you have even less measurements, right?
So let's thank Tamer once more. And I'd like to present you with this as a souvenir of this event. Congratulations.
Thank you so much. Thank you very much.
Thank you all very much for joining us. Thank you.